So the final unit of study, or the final piece of the puzzle for this unit of study on unit, oh, no, we're past unit 3. Unit 4.1 on magnetic forces is this thing known as the Hall effect. And you'll find in whatever textbook you read, there's an equation we associate with the Hall effect. And for the most part, we're going to ignore the equation and the computational aspect and stick to just a conceptual understanding of the Hall effect. But at least when we peek at the equation, we get the idea that the Hall effect somehow associates a current density with a magnetic field and an electric field. And we notice that there are an X, Y, and Z component. There's some sort of three-dimensional nature to the way in which current density, magnetic field, and electric field relate to one another. So let's skip the equation and speak conceptually on what the Hall effect is all about. So the Hall effect helps us determine whether the charge carriers are positive or negative. Now, what do we mean by that? So far, we've assumed that all of the current carrying devices are wires. Typically, in our homes, we use copper wire. In fine electronic circuits, there might be gold wire. But in any case, when we use a metal, the charge carriers are the free electrons in that metal, and I'm trying to picture these free electrons as little dots. Obviously, there are moles upon moles worth of electrons in a large piece of wire. So we're talking billions of electrons, and I'm only showing a few little dots. But the idea is, if these dots were to drift a little bit to the left, right? If they all have a component of motion or drift velocity to the left, each time an electron like this one vacates this region, a little bit of negative charge has transferred from here over to here. And so the end effect now is this little region right here is now positively charged. However, this electron ultimately will fill in that region, and it's negative, and this positive will cancel each other out. And now this region is slightly positively charged due to the electron that vacated. But then this electron fills that in, and next thing you know, this is positive. So as these negative charges are drifting with a velocity to the left, we get the appearance that positive charge is being transferred to the right, and that's what we call conventional current. And so we say, even though the electrons have motion to the left, this thing we're calling the current, the flow of positive charge, is to the right. They aren't actual positive charged carriers, it's negative charge carriers drifting to the left that gives us a current to the right. However, there are some devices, in particular semiconductors, that have been, that we call P-type semiconductor. The P stands for positive. P-type semiconductor material has positive charge carriers. And so what they do is that they imbue the, they call it doping, right? They've added some impurities to the semiconductor material. Silicon and germanium, I believe the chemical symbol for germanium is Ge. Those are the two most common semiconductor materials that can be doped with other materials, and if you dope it with positive charge carriers, then positive charges that drift to the right through the semiconductor would constitute a current that flows to the right. So we can definitely identify when current flows to the right or the left. All we need to do is place the wire in a magnetic field, maybe that points into the page, and if I find that a wire placed in a magnetic field pointing into the page experiences a force. Let's say, for example, I know when I place this current-carrying wire in a magnetic field, I see the whole wire gets forced downward. Then the question is, what was the direction of current? Why don't you take a minute and use the right-hand rule and see if you can figure it out. The force on the wire is down. The magnetic field points into the page. So point your fingers into the page. Make your palm face downward. This would be an example of a current that's flowing to to the left. So the question goes, is that because positive charges are drifting to the left, or is that because negative charges are drifting to the right? That's where we get back to the Hall effect. The Hall effect will help us answer the question of whether the charge carriers are positive or negative charge carriers. So let's see how that works. Let me draw a slightly larger version of this conductor whose current is flowing to the left. Now let's say indeed this is a typical wire, like made of copper, and so the reason we have current to the left is because little negative charges are drifting with some velocity to the right. Now remember, we were talking about placing this wire in a magnetic field that points into the page. So why don't you do this? Why don't you point your thumb in the direction of the velocity vector. All right, point your fingers into the page. Now, keep in mind, electrons are negatively charged, so because your knuckles are facing downward in this example, the result would be that the electrons end up down on the bottom part of the wire as they conduct, or as they drift with some velocity to the right. And because the electrons get forced toward the bottom of the wire, that means the top of the wire is positively charged. Well, if you have a alignment of negative charge along the bottom of the wire and positive charge at the top of the wire, then there's an electric field that gets induced across the width of the wire. And that electric field points downward in this case. Now, if we come back to here, we can say that the magnetic field is maybe on the z-axis. That's our magnetic field. And then this velocity is along the x-axis. And so the electric field is on the y-axis, right? These are three mutually perpendicular directions. The b-axis is aligned in and out of the page. The electric field is aligned from the top to the bottom of the page, and the electrons are drifting from the left to the right on the page. So you can maybe get a little more appreciation for this equation that we were ignoring. The current is along the x-axis. Okay, magnetic field, I can change my frame of reference and say magnetic field is the y-axis and electric field is the z-axis, right? Just as long as I have three mutually perpendicular axes. So when we scroll back up, yeah, electric field on the z-axis, magnetic field on the y-axis, current on an x-axis. So by noticing the polarity of the electric field lines point down, then if I were to take some sort of device that measures potential difference, like a voltmeter, and hook it up across here, my voltmeter will tell me the polarity, positive compared to negative. Now let's check out the other case. I have a magnetic field that points into the page, and the other case would be positive charges are drifting with a velocity to the left, and that's the reason why the current flows to the left. Either way, current flowing to the left could be due to electrons drifting to the right or some positive charge in a doped semiconductor drifting to the left. So let's apply the right-hand rule. Point your thumb to the left, point your fingers into the page, and you'd find in this case, instead of negative charge piling up across the bottom of the wire, positive charges go to the bottom of the wire, right? Meaning negative charge is at the top of the wire, and then this time the electric field across the width of the wire would point up. So by noticing the polarity across the width of the wire, you can determine whether or not the charge carriers are positive or negative charge carriers. That's the concept behind the Hall effect. And we'll leave it at that. No need to get into any computational analysis of it. Just understand that there is a very easy experiment that can be done to determine whether the charge carriers in some conductor are negative or positive charge carriers. Yay, Hall effect.